He's the one who's going to talk to us a little bit about primordial black holes. Yesterday, Farinaldo introduced us a little bit about dark matter production, the mechanism of freeze out, and today we welcome him, Professor Zapata, to this lecture. And please.
Okay, thanks, Ze, for the introduction. I would like to thank Farinaldo for these kind invitations to be here, doing collaboration, a research collaboration with him, with all the group. So it has been a very nice stay. And also thanks for the invitation to present my recent work about primordial black holes and dark matter. So for me, black holes is one of the most amazing subjects in physics, but for sure dark matter also is. So this subject is quite appealing for me. So the idea is the idea of these two lectures is uh, to address the role that primordial black holes formed during the early universe can play uh, regarding the dark matter, regarding the evolution of the universe, and in particular with the role of connected with dark matter, the dark matter abundance. This means that I am not going to consider black holes, primordial black holes, as dark matter. Okay, so that will be clear after. So now here I'm going to consider these primordial black holes as a second production mechanism, dark matter production mechanism. Okay. These lectures, there are a lot of, I will say, good reviews in the archive. So I just want to mention a few of them. Mm. These reviews are for inflation plus primordial black holes. This, all of these are for inflation plus PBH. And I would say all of them consider PBH as dark matter, but for formation, it's good for us to consider them. Okay. Then two more papers about okay. These are dark matter of PBH as a dark matter production. Mention this. Okay. So I'm going to base on these two papers to describe the the primordial black holes as a dark matter production mechanism. Okay. So to start with, just a few comments about black holes in general. We have that black holes. We can define black holes as a region of the space-time that is highly curved and is empty, and this and they are defined by a surface that we call horizon event. even this is the RS, that is the Schwarzschild radius, and is equal to 2GN M over C squared. I'm going to use natural units, so for me, Z is equal to 1, okay? And M, from the Noether theorem, all the black holes can be described by just three numbers: the mass, his charge, and his spin. So in these lectures, I'm going to focus only on black holes that are neutral and do not rotate. Black holes do not rotate. So Schwarzschild black holes, okay? So let's forget these two quantities. Um, okay, this something to remind. The Schwarzschild radius can be written down as this is approximately. I would like to check. This is around 10 to the minus 28 centimeters and black hole over 1 gram. Okay, so for PVH, for black holes, whose mass, which mass is of the order of 1 gram, the Schwarzschild radius is over 10 to the minus 28. For black holes of the order of 10 to the 8 grams, that means 100 tons, that this kind of black holes are of interest for us because it's the maximum allowed value for the black hole mass that we are going to consider. If, for example, okay, for M black hole equal 10 to the 8 grams, so our Schwarzschild is 10 to the minus 20 centimeters. So this is a Schwarzschild radius less than the, I would say, 5 orders of magnitude less than the size of the proton. Okay, it's quite small. If the mass of the black hole is, I would say, for example, the Earth mass 10 to the 17 grams. 17 grams is of the order of 10 millimeters. Okay, and for the sun, the Schwarzschild radius is of the order of 3 kilometers. So you need to compact all the mass of the sun in a sphere of with a radius of 3 kilometers to form a black hole. Okay, important. The black hole is made of space-time, vacuum space-time. So if you use your hand to try to touch the black hole, you don't touch anything because it's space-time, vacuum space-time. Okay, it's just curvature. Good. So these masses we can there is a raw classification of the black holes in terms of their masses. So for masses below 1 point solar masses, these are mini black holes. for masses between one solar mass and 300, we have stellar black holes. Okay, from 300 to 10 to the 5, we have intermediate black holes. And finally, for masses larger than 10 to the 5, we have the supermassive ones. Okay. The ones that we are interested on are those with masses much more lower than 0.1 solar masses. So the ones that we are interested on belongs to this category, and in particular, we are going to consider from 0.1 grams PBH less 10 to the 8 grams. From 0.1 grams up to 10 to the 8 grams, 100 tons. Question, how much is, in order to put some insight, how much is the Planck mass in terms of grams, in units of grams? Because for particle physics, or particle physicists, the Planck mass is a huge energy. So how much is the Planck mass in terms of grams? Remember that the Planck mass, the reduced Planck mass is the one that I'm going to use, is 2.34 times 10 to the 18 GVs. Okay? In grams, this is the order of 4 10 to the minus 6 grams. Okay? So, is 4 millions. The ones in our galaxy is 4 millions. The ones in M87 is around 6,000 millions. Okay, so they are in the range of, they are supermassive black holes. Okay, and notice this. Notice that the stellar ones are the ones that can typically be formed by a stellar collapse. Okay, good. So in principle, we have an explanation for this kind of stellar, for this kind of black holes. For those, so yes, it's the explanation is not settled at all. Okay, so now let's move on to how primordial black holes. I'm going to say primordial and primordial black holes and black holes. For me, is both are the same. Okay. Okay. How we can create primordial black holes in the early universe? Because for sure we know how to produce black holes by a collapse of a star, but how to produce black holes in the early universe? So basically, we have to generate regions with an overdensity, and this overdensity then collapses to a black hole. That is the key point. This is the primary mechanism for production of primordial black holes. There are a lot of production mechanisms, but I'm going only to discuss briefly this kind of production because I am going to be quite agnostic regarding the production of black holes. Okay, but to have some intuition in how to produce black holes in the early universe, so let's consider uh, formation in the early universe for sure. So the idea is we have uh, the uh, uh, the density that this and this density can fluctuate. The fluctuations are given by delta rho, and we need that these fluctuations be of be high intense enough or be large enough in order to generate black holes. What is the condition for a fluctuation to collapse into a black hole? Into a black hole, the condition is that delta rho must be larger than the. Uh, let's remember that in the early universe, the universe is populated by radiation. What is radiation? It's a gas of relativistic particles. Okay, for example, photons, neutrinos, and all the standard model, because at high energies, at high temperatures, the masses of the standard model particles basically uh, are zero in comparison with the kinetic energy, right? So all the standard model behaves as radiation at high energy. So the standard model at the early universe is populated by radiation. Okay, so the fluctuations must be larger than the pressure due to the radiation. Okay, let's remember that radiation generates. Let's remember from the electricity and magnetism course that a photon generates a pressure. Okay, generate pressure. So this this overdensity must be larger than the pressure due to the radiation. And for a perfect fluid, let's remember that pressure is equal to omega rho, and the rho is the energy density, and omega is the parameter that enters in the equation of state. This is a equation of state. So for photons, for radiation, omega is 1/3. So this is very well known from the electricity and magnetism courses. Okay, so this means that delta rho, that delta equal to delta rho over rho must be larger than 1/3. That is basically the condition for these inhomogeneities, these fluctuations in the density to collapse. Okay, so the gravitational pull overcome must overcome the pressure due to the radiation. Okay, so but we have to the typical we have to guarantee that these fluctuations have the we have to wait that for these fluctuations to enter to the horizon. I'm going to explain in detail what does it means. So these fluctuations, when we pass to the Fourier space or momentum, we can this fluctuation. I'm going to put this. This is delta critica. this is delta critical. Then we have here then we can have some perturbations. Okay. The size of this perturbation is characterized by some wavelength from some a distance. Okay. So let's put it in this way. And this distance, I'm going to this the perturbation scale for me is going to be lambda prime, lambda equal to 2 pi over k and equal to 2 pi over k prime. K and k prime are the modes in the Fourier space. Okay? So, this is when these fluctuations are formed. In order to see when these fluctuations collapse, we need to introduce the horizon moving scale. Horizon scale. So here I need the I'm going to discuss briefly the Freeman-Lemaitre-Robertson-Walker cosmology. Okay, so the Freeman-Lemaitre-Robertson-Walker cosmology can be described to the corresponding metric is ct square minus 80 square dr square plus. Okay, let's put it. Okay, this is the Freeman-Lemaitre-Robertson-Walker metric. K here, K can be 1, 0, minus 1 for flat, for open. Let's put in, this is close, and open. Okay, for the three kinds of universe with a spherical geometry, an hyperbolic geometry, and a Euclidean geometry. When we introduce the corresponding this metric in the equations, the Einstein equations, and examine the 0, 0 component, this leads us to the Freeman equation. The Freeman equation is h squared, that is a dot over a equal to so this is a squared. So for me, for now, I'm going to choose the flat space because that is our universe, and for simplicity purposes, okay, I'm going to neglect this term. So I'm going to choose a flat universe. Okay, so this equation is quite important because relates how this is how the space time is expanding or contracting depending on this is the energy density, of the particles that are populating the universe. Okay, so we have also, this is the Freeman equation. We have also the energy conservation, that is the covariant derivative of the T mu nu, where T mu nu is the energy momentum tensor. I forgot to write down here. So T mu nu is equal to U sub nu minus rho plus pressure minus pressure G mu nu. Okay, this is the energy momentum tensor for a perfect fluid. Then this equation give us 0. Then from this we have that rho naught plus 3 a dot 8 rho mass p equals 0. Need to check. Yes. Okay. Let's remember that. So here we have an unknown variable that is 8 rho and pressure, and we have only up to this moment two equations: the Freeman equation and the energy conservation. We need a tier one. The tier one is the equation of state. So this one. Okay, let's put it here. P is equal a function of rho. In particular, for a perfect fluid, we are going to use omega equal rho. So for is equal to 1 tier for radiation, 0 for matter or dust. For us, matter is a non-relativistic dust. Okay, radiation is relativistic. And finally, -1 for something that we call dark energy, and in the most simple case, vacuum energy. Okay, vacuum energy, or lambda for cosmological constant. So let's remember that for the case of matter, there is no pressure at all, because since they are non-relativistic, so the pressure is basically 0. Then, so replacing this omega, p, and rho in this equation, we end up with for matter, rho matter scales with the scale factor as rho matter 0 over the scale factor to the 3. And rho radiation scale as rho radiation 0 a over the a0 over to the 4 power. Okay, this means that if we plot, for example, logarithm of a over a0 as a function of rho, so or log what do you expect? So for the case of radiation, this line with a given slope, but for this is for radiation, but for matter we have that a lower slope. This means that with time matter will dominate. Okay, good. And for vacuum, the only thing that you have to do is to sit and wait, because since it's constant, this is lambda. This is the reason why our universe now is becoming vacuum dominated. Okay. Okay, so taking into account this, so so we have that um, so raw radiation is 1 over 8 to the 4, raw matter is 1 over 8 to the cube. So let's put this expression in the Friedman equation, and in this case we have that solving the Friedman equation, that A behaves as t to the evolves as the square root of t, and this means that h is equal to 1 over 2t. So h, let's remember that h is the derivative of the scale factor normalized with respect to time, normalized by the scale factor. So, and let's remember that h denotes the typical size of the universe in that moment, okay? 1 over h, concretely. And for matter, we have that in this case, h, a is t over 2 thirds, and then h is 2 thirds 1 over t, okay? And so h is 1 over h is the typical size of the universe at some time t, okay? So let's remember that the physical distance, this is a h over 1 over h is the physical distance. So in general, we express the physical distance as the moving distance times the scale factor. The moving distance, for example, for two galaxies in our universe remains constant, the moving distance, okay? But the physical distance for sure is increasing, is varying because a is a function of time, okay? So let's let's divide the Hubble scale by a in order to determine the horizon moving scale, okay? So 1 over h times a to the minus 1 is the moving horizon scale. Perfect. And something that I also need to mention is that when the universe is vacuum dominated, since rho is constant, because yes, because is in the case of the vacuum energy, the energy density remain constant. So h, in this case, h is h lambda is also constant. Okay, so during a vacuum energy dominated era, the Hubble rate remains constant. Good. So now I'm going to plot the moving or scales as a function of the scale factor. We are going to understand where the primordial black holes form. So log of A. So what is the, during vacuum domination, let's remember that during inflation, inflation is a epoch where the universe was dominated by some kind of vacuum energy, but this vacuum energy, in some sense, ends stops to dominate. So we don't usually don't call it vacuum energy. We call it inflaton. Okay, so inflaton, inflation is a epoch where during the very beginning of the universe, where the effective equation of state of the universe was -1, like a vacuum energy. Okay, so this is the end of inflation. This is the end of inflation. End of inflation. So if I want to write a times h to the -1, how it is the figure, the corresponding figure. So since h remains constant during inflation, so this is just 1 over a, and the logarithm is minus the logarithm of a. At the end, we have this. Okay? This is the co-moving horizon scale during inflation. Then let's remember that the end of the inflation is described, in general, inflation is described by a potential where phi is the inflaton, and the potential is quite flat, quite flat during inflation, but then this potential goes as this, and the inflaton. So here, the inflaton slowly rolls and then start to oscillate. And then here is what we call reheating. This is the end of inflation. So the end of inflation is here, and this period when the inflaton is oscillating is what we call reheating. And the inflaton in this era decays into, for example, standard model plus standard model particles. Okay, and since this guy has a lot of energy, stored energy, so this energy is converted into radiation. So at the end of the inflation, the universe becomes radiation dominated. So this means that uh, the community scale goes as, let's remember that for radiation, H is 1 over T. So at the end, H goes as, look this, 1 over T, but T is 1, this is A, goes as A. If A to the A square. Okay. So, no, A goes as A. Okay. It's A squared, but so this means that at the end, for radiation, 1 over A times H is A. Good. So now we have with the same slope radiation, then this ends up to the time of equality, when matter, the energy density associated with matter is equal to the energy density associated with radiation. This is a matter radiation, radiation matter. Okay, then matter, the slope is a bit lower, and then again, this is a matter lambda. And then again, a vacuum, almost vacuum dominated era where the slope is negative. Okay? So now let's let's consider some specific scale. For example, the scale associated with a perturbation. Okay? Let's remember this, that this scale is associated with k, that is k is a co-moving wave number. Okay, it's a co-moving wave number. So I'm going to draw here. Okay, this is a k. K equal to uh, um, k equal to 2 pi over lambda. So at the end, I'm going to put k to the minus 1. This is the scale, a typical scale. And since it's co-moving, okay, since this is co-moving, this wave number doesn't change with A. Then, so I'm going to draw this. This is k to the minus 1. Let's put it here, PVH. Okay, this is the typical size of a fluctuation during inflation. Okay, this perturbation was made during inflation. Okay, and the typical scale of this fluctuation is 1 over k, right? Let's remember that all this curve is the horizon co-moving scale. So from here, notice that in this region, this scale is less than the horizon co-moving scale. So this scale is sub-horizon, sub-horizon, sub-horizon. And the same happens for a region in the right hand side of this line. Here we have that k minus 1 is larger than is lower than ah to the minus 1. Okay? So it's sub-horizon. But in this period, the typical scale of the fluctuation is larger than the horizon scale. So basically, there is no collapse at all. You have to wait until the typical scale re-enter to the horizon. Re-enter to the horizon is when this line crosses with this line. So in this point, the fluctuation that was originated during inflation here or before here, this fluctuation only will collapse after this point. Indeed, in this point. Okay? So here we have that. Here we make a zoom, we will see primordial black holes form in that point. Okay? And notice that the ones with a typical scale, yes? typical. Okay, so this is a fluctuation on density, but this fluctuation has a typical scale. Okay, for example, if you think of in terms of Fourier transform. Okay, so you have several modes, and there are some modes that contribute more than the other ones. Okay, so this typical scale is this one, k 1 over k. Okay, the main scale. The point is that this typical scale of this density fluctuation, this overdensity, is like if you are in a swimming pool, and the wavelength of a wave is kilometers. You don't feel anything. Okay, you have to wait until unless the swimming pool is like the sea. Okay, so the same is happening here. Okay, so you need to wait until the mode enters, re-enters to the horizon. Okay, so after this point, the horizon is larger than the typical the scale associated with the fluctuations. So in this point is where the primordial black holes form, and notice that they are formed during radiation domination. Okay, and look all the way up to this point. Okay, this point when the energy density associated with radiation is equal to the energy density associated with matter, take place a redshift 3,300, or a t around 50 kiloyears. Okay, this is the age of the universe when both these two contributions are were of the same order. Okay, good. More questions or any question? So the key point here is the fluctuations are made during inflation, but they collapse during radiation domination. Okay, after the typical scale re-enters to the horizon. Okay, good. Something more to say here? Yes, there is a lot of things to say here, but I don't have too much time. But okay. Okay. Good. Let's continue. Can remove this. Good. So this means that this condition means that the black holes form with a typical mass given by the mass that is enclosed by the Hubble horizon. So the form that with the initial mass of the black holes that form here is the typical mass associated with the one that is enclosed by a Hubble volume. So the initial black hole mass, I'm going to define it in this way. M in is equal to some small constant gamma that is 0.2 of the order of 1 gamma, and the mass enclosed by the the Hubble horizon is just the density times volume, right? Which density? The one is dominating the universe. So radiation. Okay, radiation. What is the volume? Okay, the volume is gamma. Gamma, this is the order of zero point 0.2. Strictly speaking, is omega to the third over 2. Okay, where omega is the parameter of the entering in the equation of state for radiation. Okay, so and volume is 4 thirds times pi, and the radius is the Hubble 1 over h. So this h to the minus 1 to the third power, okay, because it's the radius to the cube. Okay, good. So we have, fortunately, we have the Freeman equation where h is equal to rho radiation over 3 Planck mass square. This equation is the same. Is this one? I am using the reducing Planck mass. One over time or one over length, because c is equal 1. Okay, good. So this is h squared, and what is the energy density associated with radiation? So do you remember the Stefan the Stefan Boltzmann law, that the energy density radiated by the sun is proportional to temperature to the 4, right? So it's the same. P squared over 30 G star that depends on the temperature times T to the 4 power. This will be sigma in the case of the Stefan Boltzmann law. However, in the case of the Stefan Boltzmann, we had only photons. But in this case, at high temperatures, we don't have not only photons, but also neutrinos, quarks, leptons, gauge bosons, etc., etc. So at the end, this number is not 2 due to the 2 degrees of freedom to the spin polarizations of a photon, but is 106 times 75. So this number is okay. That is the general Stefan Boltzmann law for radiation during the early universe. Good. This point. Okay. Okay. When the look the change of slope here ends the radiation dominated era and starts the matter domination era. And then when the vacuum energy starts to dominate. Okay, this corresponds to a redshift 0.7, this one 0.7, and a t around 10 gigayears, 10 to the 10 years. Okay, 10 to the 10 years. Okay, good. So this means that I have and notice a key connection. Here we have H in terms of temperature. Okay, so at the end, H goes as T squared, right? However, we know that in a radiation-dominated era, H goes as 1 over T, time. So this is proportional to 1 over time. So through this connection, we can talk in terms of temperature or in terms of time. Okay, through this expression, we have the connection. Good. So at the end, ME can be put it in this way: 10 to the minus 15 grams T, 10 to the minus 30, 10 to the minus 23 seconds. Okay? So, primordial black holes with T in equal to, for example, 10 to the minus, the ones that we are interested in. For example, the ones that are formed when T is equal to QCD, the QCD phase transition, that is the order of 10 to the minus 6 seconds. So this means that Mi, the initial mass, is of the order of 10 to the 2 grams, right? 10 to the 2 grams. No, no, it's okay. No, maybe this is plus. Yes. Let me check. Yes, definitely plus. Okay, so at the end is 17, 6, okay, 17, 32. Okay, 32 grams. 32 grams, let's remember that the solar mass is of the order of 10 to the 30 kilograms, 10 to the 33 grams. Okay, so this is of the order of 1 solar mass. Okay, primordial black holes that are formed by the QCD phase transition have a mass of the order of the solar mass. Okay, and the ones, let's remember that Farinaldo taught us last lecture that we have measured pretty well the the abundance of the light nuclei. That is what we call Big Bang nucleosynthesis. So we cannot touch Big Bang nucleosynthesis. So these primordial black holes at most must be formed at or just before Big Bang nucleosynthesis. So these guys, T in equal to T BBN, this is 1 second. BBN occurs when the universe has only 1 second. So this means Mi is equal to 2 grams. This means 10 to the 5 solar masses. Okay. But there are other ones, others that I am interested on. For example, Ti equal to 10 to the minus 39 seconds. Okay. Second. This means that Mi is equal to 0.1 gram. Okay, 0.1 gram. A primordial black hole that was formed when the universe has an age of 10 to the minus 39 seconds Okay, the mass is the corresponding mass is 0.1 grams, and uh, and also for oh, okay, I, it, it's okay. Okay, yes. Okay, so now, that is a question that I'm pretend to address in the following. Okay, but at the end, it depends on the formation mechanism. Okay, it could be uh, due to density fluctuations, to collision of bubbles, due to phase transitions, to domain walls. There are a lot of mechanisms, and so at the end is model dependent. We in For us, we will be agnostic regarding what is the number density of black holes, how many black holes will be formed. Okay, so it just we will parameterize through a parameter, dimensionless parameter. Okay, so this is T. Okay, so and notice that all the black holes are formed under these assumptions. All the black holes are formed with the same mass because all of them have formed at the same time. Okay, at the same time. The time determines the mass. Okay, for sure you can consider production mechanism when you don't have where you don't have a monochromatic distribution. Monochromatic means one single value for the mass, but instead a distribution. But okay, the simplest case is a monochromatic distribution. Okay. Fanina, should I stop or I can continue? Yes. Okay. Time for questions.
Anyone, does anyone have any questions? I have one.
Oh, just please.
What causes the uh, difference in pressure? Pressure, no, sorry,
So
intensity.
these
Yeah,
fluctuations.
what's the cause of it?
Okay. Thanks for the questions. Very good questions. The simple case is we know that mm, notice that these fluctuations are made during inflation, where the size of the universe was rather small. So in that epoch, quantum effects are very important. Okay, and you know from the uncertainty principle that quantum fluctuations are everywhere. Okay, so these fluctuations are could be the ones that generate over densities or fluctuations on the density of the perfect fluid. Then, thanks to the inflation, these uh, micro fluctuations become sizable because the inflation is a era where the scale factor is grows exponentially. So the micro scales become macro scales. So the simple explanation is the simple, but not the correct one, because this is something to mention. Look, if I plot here the scale of the CMB, okay, let's draw the typical scale of the CMB. a typical scale of the CMB is this one. And here, the fluctuations associated with the CMB and re-enter the horizon here. Okay? Good. This is K to the minus 1 CMB. Okay. We have that the power spectrum of a Fourier transform goes. This is proportional to this correlation. Okay. For the CMB, pk is of the order of 10 to the minus 9 here. pk CMB is the order of 10 to the minus 9. And in other words, I think you mentioned it yesterday. What are the difference on temperature in the sky when we are talking about the CMB? It's of the order of 110 microkelvin, 10 to the minus 5. Okay? 10 to the minus 5. And notice that here, so in the CMB, we need this of the order of 10 to minus 5. But here, we need of the order of 1. Okay? So just quantum fluctuations are not enough. You need special conditions in order to generate overdensities of the order of the same density. Okay? Look that here we have fluctuations of 1 part in 100,000. Here you need of the same order. Okay? So the probability, I would say in that case, is quite small, rather small. Okay? So yes, quantum fluctuations, but you need to tune. Okay? At the end, you need to tune. Okay. More questions?
Any questions?
Please don't be shy.
Don't be shy. You have to.
There is any way that we could premeditate this from happening, like the moment that the first point happened. There is there is any way that we could premeditate this from happening.
This point
The second one,
here.
yeah.
Okay. Very good question. So how do we prove the existence of a population of primordial black holes in the early universe? Right? How to prove it? So it depends, but for me, one of the most exciting ways of proving primordial black hole is through gravitational waves, because primordial black holes, as we will see next lecture, evaporate. Primordial black holes evaporate, and the evaporation involves, for example, gravitons, and these gravitons will form a stochastic gravitational wave spectra. So you can, if you detect this kind of gravitational waves at very high frequencies, the ones coming from Hawking radiation take place at very high frequencies, above 1 kilohertz. And notice that there is no astrophysical phenomena known that can produce gravitational waves above kilohertz. So if we detect gravitational waves in that window, the most, I would say, with high probability is from the early universe. Okay, that is quite exciting. And, and also, for example, we will also discuss, we have to determine, that is also subject from of the next lecture, this if we produce, if the number density of primordial black holes is quite high, what happens is the radiation era, this one, ends quickly and then becomes matter dominated by primordial black holes, for sure must be after this point, because in this point they are formed. Then, for example, here, just after they are formed, they start to dominate, okay, and then evaporate again, and evaporate into radiation, okay, then radiation. So we can, in this way, we are altering, we are changing the standard cosmology. The standard cosmology is that after inflation, we have radiation domination up to this point. But if we change the standard cosmology, we can expect, for example, other some deviation in some observables in principle. For example, we can, if dark matter is produced during primordial black hole domination, so for sure the wind paradigm, the typical values required to explain the dark matter through the wind mechanism will be different. That is the subject of the next lecture. Okay. More questions? Ricardo, thanks for your question. Don't fight, please.
Okay. How does primordial black holes influentiate in the BBM?
So they cannot. Otherwise,
No, but
you will have a different abundance from the light elements. So they must these primordial black holes must evaporate before BBN.
no, but the way it influentiates.
Okay, good. So since the Hawking evaporation is a gravitational process, so all the particles with mass, with energy are part of the Hawking radiation. So the evaporation products, uh, within the evaporation products, we find indeed not only photons, neutrinos, but also electrons, positrons, protons, neutrons, etc. Everything depends on the temperature of the black hole. The black hole can only radiate particles with a mass lower than the temperature of the black hole. Okay, the point is that the typical temperature of a black hole evaporating by the time of the BBN, the typical temperature in units of GeVs, that is the units of particle physics, is of the order of 10 to the 5 GeVs, sorry. So that is 100 TVs. So basically, you can produce all the standard model. So you will spoil immediately the abundance of the light elements. So you have to stop the evaporation at that moment. Good.
So I was wondering, like last week we had the lecture from Glaube who talked about phase transitions, and one of the way of detecting them were from gravitational waves. So
Right.
how do I know if the gravitational waves came from primordial black holes or phase transitions?
Okay, that is a very good question. So indeed, gravitational waves associated with PBH, we can there are a lot of types. I mean, there are several mechanism in how to produce them. At least 4. So each of these production mechanisms generate a particular gravitational wave spectrum at different frequency, okay, and with different amplitude. So how to discriminate? I don't know, and I will say it will be quite hard to disentangle. Yes, because and there are a lot of things that must be assumed at the time when you are determining the gravitational wave spectrum. So at least to be clear, I don't know. Right. 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 Okay. Thanks for your attention. See
Okay,
you
everyone,
tomorrow.
thank you for today. Let's please thank the professor, and I hope to see you all tomorrow.